Bonjour. Le déjeuner, c'était bien? But I will stop speaking French because whenever I'm in France and try to speak French, I'm getting into trouble. I remember the last time I was at a French conference, I wanted to say ça marche, and incorrectly I said c'est marche, and people understood c'est mouche. And then it was super confusing, and I decided it doesn't make any sense, so we'll stick to English. You'll have to live with my English. So I'm Philipp, and I want to talk a bit about trade-offs in data stores and where we can take them. So I work for Elastic, the company behind the Elasticsearch. You might have seen that one. Looks something like this. Maybe you've met my French colleague, David Pilato. I always say I'm the younger and German-speaking version of him. Because he's doing a lot in the French region, but he's busy today, so I've kind of taken over for him today. So what is the perfect data store? What is the answer for that? Normally, you would probably say something like, it depends, especially when you're a consultant, right? And then you would start charging a lot of money, because that's normally what you do. So it depends, and this will be a very important answer. You need to remember this. We will get back to this it depends a couple of times today, because it really depends. You mostly need to pick your trade-offs, and that is really the gist of this talk, that we want to discuss, like, what are the trade-offs that you do in data stores and do you have in your systems. And sometimes people promise you magic, and that their systems are magic, but there is no magic, and it doesn't work like that, as we will see. So who knows the CAP theorem? That's not everybody. So the CAP theorem is one of the most widely known trade-offs in data stores or distributed systems in general. It's based on this paper, and the basic idea is you have 3 attributes that you want to have, and you can have 2 at most. And you need to pick what you want to have. And if you don't pick it explicitly, something random will happen. And you normally don't want that. So the 3 trade-offs, or the 3 attributes that you want to have, are consistency, availability, and partition tolerance. Consistency is total order, basically. So it is, you have a distributed system with multiple nodes working on a problem, but it looks as if you were talking to a single system, and all the operations were in a single order, so one exactly after the other. So you have a total order of operations. So if you ask the entire cluster of nodes for a specific question or request, they will always give you the same answer at one point in time, regardless of which node you query, for example. The next attribute you want to have is availability. Availability is, as long as you can reach a node, it will answer your question. So a node cannot decide, we're in a weird state, I'm not going to answer you. It has to answer. And finally, partition tolerance, this is pretty much losing arbitrary messages, or it's like you have 3 nodes and they break apart, and then you have 2 nodes on one side and 1 node on the other side of your cluster. And that is when you need to make the decision of which attribute you want to have. So to draw this out, you have something like this. You have these 3 attributes, and you can see there is nothing in the middle. And your systems can only decide which 2 attributes do you pick, because you cannot have all 3. By the way, if you take some other trade-offs or you design your system badly, you might only have 1 or 0 of these attributes. So it's not guaranteed that you have 2 always. It's just, this is the only possibility. And the paper in general is pretty simple, because it's not lots of math, it's very descriptive, it just describes. Let's assume we have 3 nodes, and they break in the middle, and you have 2 nodes on one side and 1 node on the other side. And then you write some data to these 2 nodes, and then this other node has to decide, because we have this network partition, so these 2 nodes cannot see this other node. You write data here, and then this node has to decide, am I available? So I'm answering a query, but I might not be consistent with the other 2 nodes because I lost the connection to those. Or is this system consistent? Then it's not answering because it's not sure what the other 2 nodes have in data, but then it's not available because it's just not answering the question. So that is the general idea of the CAP theorem. One misconception is that partition tolerance is something you can decide on having or not having. Normally, if you have not seen a partition in a distributed system, it's either because you have been very lucky or because your monitoring is not good enough. That's the other option that you normally have. And the other misconception is that there is consistency in ACID, like the transactional sense, and the CAP theorem. And those 2 consistencies are different things. So the consistency in ACID is pretty much moving from one correct state to the next. So you have like a not null constraint, and you move from every operation moves the system forward, and you don't violate the not null constraint. Whereas the cap theorem, it's kind of like this time linear thing. So at one point in time, you have one view over the system. If you want to sit, we have plenty of chairs in the front. Don't be shy, we have space. You don't have to stand, but you can. And if you want to explain the cap theorem to your kids or your parents, you can do that with Robinson Crusoe. So I think Robinson Crusoe was English, and he was partitioned on his lone island. So he was kind of in a network partition. And let's assume a ship comes by and asks him a current question. And then he has to decide, am I consistent or am I available? Because if he answers, he might give an outdated answer because he has been on his lone island for a couple of years already. So if you ask him who is the king or queen of England, he can give the best answer he has, but it might not be consistent with the rest of the world. So is available but not consistent. Or he can decide he's not answering, then he's consistent but not available because he's not answering. So that's kind of the trade-off explained with Robinson Crusoe. Does anybody recognize the island? It's from a movie from the last couple of years. Yes, Star Wars is good. It was this Star Wars. So Star Wars versioning is very confusing, but we'll mostly stick to Star Wars examples. That what we'll do. By the way, you can break the cap theorem with def null, because that's always giving you the same answer. It's kind of consistent. And that still doesn't make it a very useful system, because it always just throws away your data. But this kind of breaks the cap theorem. But most other things don't break the cap theorem because it's a very generic decision that you have to make. Okay, so that was the cap theorem. And then we have internally this so-called fab theory. That is kind of the same idea. We have the attributes fast, accurate, big. And again, you need to make the trade-off that you can only have 2 out of 3. And you kind of need to pick where you go. This is Mark. And Mark, it's his favorite hobby. He came up with the fab theory and the name for that. So the attributes that you have are fast. This is something is processing in real time or near real time. I would always say, like, if you have a query and you answer for the query to return, this is real time or near real time. So it's a human waits for the answer. It's not the batch job, you go for a coffee or you go home for the day. You wait for the answer to come back. So normally you want to have an answer within 1, 2, 3 seconds at most or so. That's the fast attribute. So that's something we normally want to have. Not all systems have that, especially, for example, if you're in the Hadoop ecosystem and you run these big MapReduce jobs, they might take minutes or hours or days to finish. There you don't have this fast attribute, for example. Then we have accurate. Accurate means I want to have the exact result. It's not an approximation, it's the actual result that I want to get out of this. And finally we have big. And big is always complicated to describe here. I will stick to something that is parallelized. So it's something that I cannot run on my laptop, even though I will run my demos on my laptop. But in theory, the idea is something so large that you cannot run it on a single machine, so you need to parallelize it. If you want to talk about big data, I'm not a very big fan of that term, because by now it's mostly buzzwords. And yeah, let's just ignore big data as a term. Let's say anything that we need to parallelize will fall into that category that we have with big. So I guess fast is clear. You wait for the answer to come back. Big, you need to parallelize, is also pretty clear. What are the trade-offs around accurate? Like, what would a system, how would it be helpful if the answers are not correct? And we look at some trade-offs and things where maybe approximate answers are good enough for what you're trying to do. So obviously we are using Elasticsearch, but this will apply to lots of other systems as well. And the only thing that you need to know about Elasticsearch is that how we scale is so-called shards. So we have an index which is kind of related data, and we can break that index into multiple pieces, each called one shard. And these shards can be kind of spread out over multiple machines. So this is how we scale things. So if you have 5 nodes, you could have 5 shards, for example, and each node would get 1 shard. So this is how the scaling works. Does anybody know where the term shard is coming from, or why do we call this shard? And we are, by the way, not the only ones. MySQL, for example, calls this shard, and lots of other systems also call this shard, this breaking up data into smaller pieces and then distributing those. Does anybody have a theory because I also only have a theory, or people believe in different histories of how that term happened to be. Does anybody know where the term comes from? So the story I believe in is, does anybody remember this one? Ultima Online, the game. And so what happened, what happened at Ultima Online, there was this wizard, and then there was the world trapped in a crystal, and then the crystal was broken up into multiple shards, and each shard held a fraction or a piece of the world. And then you had these broken up, and all the pieces or shards made up the entire world. And this seems to be at least one of the versions of why it's called shard. But this is just for the trivia side, why it's called shard actually. So let's look at the terms aggregation. What was the terms aggregation doing? It's basically the top n results. So let's assume we have something that appears many times, and we want to know which term, for example, appears most often. So the top 1 term or the top 3 terms or whatever. And I'm using the original Star Wars. Versioning in Star Wars is very complicated. I think by now it's called number 4, but it was the very first that came out. And somebody luckily counted how many times the different words appeared, and we're taking the top 16 terms, and Luke seems to appear 64 times, and R2 31 times, etc. So these are the terms and how many times they appear. And what I do is I create one index I call Star Wars with 5 shards. So I could split that up into 5 pieces and spread them out over multiple nodes. And then I insert documents. And what I have here is the first line is always kind of the metadata. So here I say this ends up in the Star Wars index. And then the second line is always the actual document. So I have 64 documents with word Luke. And afterwards we will do a count how many times does Luke appear. So we have 64 documents with Luke, 31 with R2, etc. So this is the metadata, this is the actual document. And I've already inserted that into Elasticsearch. This is a bit like a cooking show where I've already cut the onions and prepared a bit of stuff. So we have stored the data, and now we want to run the queries. So you could visualize that as well. This would be what the visualization looks like. And this is the terms aggregation at work, basically. So you have this tag cloud, and the larger something is, the more times it appears. So you can see Luke appears most times. Does it matter if Luke is appearing 50 or 60 times here? Not really, because you just want to have a general idea. So you don't want to be totally off, but if your count is like wrong by a couple of Lukes, it probably doesn't make so much difference. But what you want to have is you want to get that answer pretty quickly. And also probably you don't want to take up too many resources. So you don't want to blow up your heap or have a lot of network transfer for that. So here we'll have some optimizations running in the background, and we're just calculating those. And we'll look at the actual query. So this is just a visualization, but we will look at the actual query behind this. So here, let's run this live so I can actually show you what is going on. I guess this is large enough for everybody to read. This is just a query. So here I'm searching over my data set, and you can see here I have 64 hits. So Luke is appearing 64 times, but I've just searched for one specific term. Now I'm running the actual aggregation that I want to run. So you can see against my Star Wars index, I'm running an aggregation. I call it most common, so I'm only looking for the most common term. Then I say this is a terms aggregation on this field, so the word and the keyword is basically we just are interested in the original keyword or in the original word. And I here have size 1, so I want the top 1 result. If I would make this size 3, we would get the top 3 results, or top 3 most common terms. And then we have this size 0 down here, which basically means I don't want any of the actual documents. I only want the aggregation, because I'm not interested in the individual documents. So when I run that, how many looks should we get out? 64. If I run that, we only get 60 looks. And I know what some of you might be saying. It's kind of not possible. Like, even with 64, why are we counting wrong? Like, what is happening here in the background? And to understand why we're counting wrong, you need to understand how we actually optimize the counting in the background. So what happens is, or normally this would not happen, but I've kind of prepared the data to show the problem. In most other cases, you wouldn't see it that strongly, but here with my even small data set, we run into this problem. So what I've done is, a document is generally evenly distributed amongst all the shards, but I've added this routing information, and this says to which shard the document should go. Basically, I take this information to make sure where it should be stored. And what you do is, you take that routing information, you hash it with a hashing algorithm, you calculate it modulo the number of primary shards, so modulo 5 in my example, and then that will give you to which shard it will go. But the first 10 documents, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, are kind of having different routing informations. All the other 54 documents go to the same shard because it has the same routing information. So our data is very unevenly distributed. And that is part of the problem why we are getting this wrong calculation. So here we are calculating where it should go. By the way, why am I hashing my routing key? Why am I not using my routing key directly? Generally, to have my data evenly distributed. For example, if you pick the routing key yourself, and you could pick, like, we could use the word, for example, itself. And then in English, the most common term is, or the most common letter is starting with E. So you could just run this against E, but then your key space might be very unevenly distributed. So the idea of the hashing function is that you will have your entire key space and it's very evenly distributed, and then you break it up into 5 similar sized chunks, the shards, and then your data will be evenly spread out across your nodes. Since I have used the same routing key many times, this is not happening here. And then you can already see when I fetch this information that some shards have more data than others. For example, shard 4 here has only 26 documents, and shard 0 has 70 documents. And I've kind of skewed that some shards have 1 or 2 looks only, and one shard will have 55 looks or so. So one shard will have many more looks. And now we need to understand how we actually aggregate how many looks are there. So what we do is we calculate the sub-result on a per shard level, but we don't calculate all the terms because that would be very expensive. Let's assume you have 1 million terms, and then every single shard would need to calculate the 1 million terms. It's like 1 million entries, and then you need to combine 1 million entries from every single shard and combine them to the total result. So the optimization that we do here is that we assume you don't need all 1 million results, because as long as your data is more or less evenly distributed, the top n results will be fine enough as an aggregation or as a close enough result. So what you're doing is, size is how many results you want to get back. You multiply that by 1.5, you add 10, and that is how many results each single shard is calculating and sending over to centralize. What was the value for size in our example? 1, because we only wanted to have a single result, so the top 1 result. Multiplied by 1.5 plus 10, how many results are we calculating for each shard? 11, 12, it's 11. We round down. So every single shard will calculate 11 results and then centralize 11 results. So 11 results per shard, and in total we are aggregating basically for 5 shards, 11 results each, so we aggregate 55 entries together. And this is how many we get. The problem is, Luke might not be in the top 11 results on all the shards, because on some shards there is only 1 or 2 Lukes, and other documents are much more common, so we are missing out some Lukes. And that's why we're calculating wrong, basically. You can actually show this. So here, this is exactly the same aggregation. I've just added this attribute, show term doc count error true. If you add this, it will show you, I know you have at least 60 looks, but I know there could be 4 more, which turns out to be the right result here. But it's basically saying, like, I got 60, like the top 11 results from each chart, I added up 60. How do I get to the error here? How do I know how many looks am I missing? Because basically I know, is Luke in my top 11 results? If not, how many times does the 11th result appear? And that is basically the error bound, because we could, the 12th position could be another loop, and there could be 1 or 2 loops, for example, missing from that chart. And that's how I calculate the error bound. And it also tells me the error bound is up to 10 in total, because this is like the last value of each single shard combined. And then there are 228 documents which are not loops, basically. So what we can do then is we can run the same calculation, but here I set shard size rather than the default of 11. I explicitly set it to 20. Since I only have 16 documents, this should give me the actual result. And if I run that, you will see we have 64 looks now. This is good. And we also have 0 error because we calculate everything. What is the trade-off here? Your query will probably take a little longer because rather than calculating 11 results each, we're taking up to 20 each. So this is a bit slower, but we kind of trade a bit of speed for more accuracy. And you can kind of fine-tune the value here, how far you want to go. So that is the trade-off you can pick there. Next up, let's look at the cardinality aggregation. What was the cardinality aggregation? That was the unique terms we have on one specific field, for example. So for example, the naive implementation of cardinality aggregation would be you have a hash set. A hash set is a data structure that doesn't store duplicates but only keeps unique values. And we just iterate over all the entries, put them into a hash set, and at the end we just run a size on that data structure and it will give us the number of unique elements. What is the problem here? How will this scale? Linearly. So both the more entries you have, the more values you will need to calculate through your hash set and try to store. And the more unique values you have, the more memory you need to have to actually store all the values. So if you have 1 million unique values, you might need up a lot of, or use a lot of memory to just store the hash map. There might be cleverer solutions. And also for unique values, oftentimes approximate values are good enough. You don't need the actual exact result. So what you can do instead is, here we're using a so-called estimator. And for the estimator, we're still hashing the value. So we hash loop, and let's assume our hash function spits out the value. So we have something 0 to 1 value range, and we have 2 digits precision after the dot. So this one would be 0.44. And what you do now is you still need to iterate over all the values and calculate that, but rather than storing the entire big hash map, we're only storing the smallest value. So we keep a single variable and we only keep the smallest value. So we hash loop, we get 0.44, we remember this one. We hash R2, this one is 7.1, we remember 0.44 because this is the smaller value. Then we run into JEDI, which hashes down to 0.01. This is the smallest value and we just remember the smallest value. Here, this is larger, so we stick to the 0.07. And then what you do is you divide 1 by that minimum value, and this gives you approximately how many unique values there are. The idea is, if you have a hash function that evenly distributes all your values, the smallest one should approximately show you how many unique values you have. The problem is that this might still be off by quite a bit and is not very exact. So there are other ways to make this work better. One of them is we are doing probabilistic counting. Here basically we hash the value, we have a binary representation, and then we take the number of unique or leading zeros. So leading, this time we're reading from the right-hand side. So you can see this one here, for example, has 3 leading zeros. And all the combinations for this one are 8. So if you have 3 bits, you have 8, 2 to the power of 3. 1 divided by 8, this is generally how many unique values there might be. Or generally 1 divided by 2 to the power of k, and k are the leading zeros that you have. The problem is this is still, depending on how your values kind of fall in this hash function, you might have pretty big jumps. So you might not want to have a single probabilistic counting method, but you might want to have multiple ones. So what you can do is, or the general idea is, this is the green curve, basically the wider one, that is the one that happens if you have a single hash function. What we want to have is, we want to have this one here. Here we are using multiple hash functions basically, and then we average out the multiple hash functions, and then it's kind of like closer to the actual value, and like it's like more more pointy curve, basically. So it's not so wide, it doesn't have that much of an error range. It's a bit pointier and more or closer to the actual value. How could you get to that kind of like pointier graph? You could just use multiple hash functions, right? And then like calculate the leading zeros for all the different hash functions and then average that out. But that will be pretty expensive, right? Because then you need to do multiple hash calculations. What you can do instead is, and we kind of simulate multiple hash functions is, and that is the idea of log-log, that you don't have just one log, but multiple logs through a single hash function. And how you do that is you basically break your single hash function into multiple so-called buckets. So you take this side here, this is basically, so you hash look. Let's assume this is the binary representation of this value or hashed value of look. Then we use the first 4 bits for the bucket and the rest to count from the right-hand side the leading zeros. So this one here is bucket 4. This one is bucket 9. This one is bucket 0. And then you count how many leading zeros you have. And then you take all the buckets and calculate what was the largest number of leading zeros. You average those out. And that is approximately how many unique values you have. And you still only need to keep like those different buckets. So you use 4 bits for the buckets and then a counter how many leading zeros you have. So you will use very little memory. That's the general idea of log-log. And then Google came along, or this is the algorithm, but we don't want to go into that part. And then Google came along and improved that, and now it's called HyperLogLog. Because their improvement basically changed the error rate to normally below 1%. So the error rate will be pretty small. And that's what they did here. So this will be very fast and still pretty accurate. That's the general takeaway of that one. And then we can calculate this. So what we have here is, we do the cardinality aggregation. And I say the precision threshold is 10. The precision threshold basically tells you up to this value, it will be exact. For larger values than this, it will be an approximation, and it might be slightly off. How many unique values did we have in our data set? 16. And if I run this, you can see now I'm calculating 17 because, well, the precision threshold is 10, so this is a bit off. This is off by 1, so this is okay. If you increase the precision threshold to 12 already, then it's already counting correctly. Because it's still an approximation, but it's close enough, and here we're using enough memory to actually make this work. So, we've seen this one. The precision threshold by default has a value of 3000, so up to 3000 unique values it will be exact. For higher values it will be an approximation. You can set it up to 40,000. For larger values we will always give you an approximation because you might otherwise blow up your heap and use too much memory. How much memory do you actually need? Basically, you multiply the precision threshold times 8 bytes, and that is how much memory that calculation needs. So this is very predictable. Regardless of how large your overall data set is, you know that you will not blow up your heap because this is how much memory you actually only use. So it's a much safer operation to run that and much cheaper. Here we have tried multiple precision thresholds and then shown the error rates. This is from our documentation. You can see with 100, you might have like 5 or even 6% of error rate. If you have 10,000, then your error rate is generally very low, like up 1 or maybe 1.5% in the worst case, but most of the time it's very, very low. So here you're trading some precision or some correctness for more speed and faster calculations and not blowing up your heap. Here this one we have already tried out and seen. Then the question can be, should I pre-compute those hashes? Because it sounds pretty expensive to always calculate all the hashes for the values. Wouldn't it help to actually pre-compute those hashes? Either you can do it in your own application, or we have a plugin called Mapper Murmur that could do that, and it would automatically store that in another field, and you could just use that hash. Is that a good idea? Exactly, it depends. That is the answer you always want to give, or not always want to give. By the way, it depends is not an excuse for not giving a good answer. It depends allows you to say like, okay, this is a complex problem, and these are the trade-offs. So you can only say, maybe this is, let's call it Philipp's law, you can only say it depends if you then describe on what it depends and what the trade-offs are. And the trade-offs here are, if it's a field with many values and has a high cardinality, then it might make sense to pre-compute the hashes. If it's low cardinality, so you just maybe have a Boolean field, for that it doesn't pay off. And if you have a numeric field, it also doesn't pay off because hashing numeric values is very fast in modern CPUs. There it doesn't pay off. If you have a large data set and a high cardinality and non-numeric, then it might make sense to pre-compute that. Otherwise, probably not. There was another paper for improvement. It was called LogLog Beta. We had a pull request and tried it out, but it didn't improve anything. So we threw away the pull request again. There's another paper that's called, or another approach, HyperLogLog sketches. We haven't implemented that one yet. So if you want to read a paper and are interested in papers, this is one of the more cutting-edge algorithms in that area. But we haven't tried that one out yet. So far, it's HyperLogLog++ that we have implemented there. And then for search, we run into a similar problem. So full-text search, what Elasticsearch does, is mostly about the relevancy. And the relevancy is normally, I query my data, which documents are a good fit for that specific query. So we could search for Luke, and here we will see something weird. So here I'm searching for Luke. And you see we have 64 values coming back, so this is expected. What is kind of weird is that we have one document here that is, so here this is my document Luke. This has a relevancy of 3.3 approximately. And then if I look at another Luke where I scroll down, you can see the exact same document suddenly only has a relevancy of 0.7. Why is this Luke far less relevant than the Luke on top? It looks as if we are calculating wrong, right? Why would one document be less relevant than the other? So to understand that one, you need to take a quick look at how full-text search actually works. So let's take a look at how full-text search works for that one. So the general algorithm that we use for search is called TF-IDF, term frequency inverse document frequency, though the current implementation has been replaced by something that is slightly improved. It's called BM25, which stands for best match 25, so it's the 25th iteration of the best match algorithm. At some point we might have a BM30 or whatever, but so far we are at the 25th iteration of that algorithm, and that proved to be a bit better. But the idea is very similar to TF-IDF, and you have three main components influencing the relevancy in your search. The first one is term frequency. Term frequency is a simple concept. It's like, let's assume we search for Luke, and one document contains Luke once, and another document contains Luke 3 times. The document that contains Luke 3 times is more relevant than the one that contains Luke once. I guess that kind of makes sense intuitively. Drawing it out on the curve looks something like this. So this is how many times Luke appears in one document, and this is how relevant it is. So if Luke appears once, it's kind of like relevancy of 2, something like that, and if it appears 5 times, let's say it has a relevancy of, oh sorry, here it has 0 point something, and there it has relevancy of 2 or so. You can see the main difference between TF-IDF and BM25 is that TF-IDF was simpler, and it assumed the more looks you have, the more important. But BM25 basically assumes once you have reached 5 looks in one document, it doesn't make much difference anymore. So we kind of cut off the curve a bit there. The next thing is the so-called inverse document frequency. The inverse document frequency assumes over all the documents you have in that field, the ones that are more common are less relevant. Or putting it another way, what is rare is valuable, which also makes sense, I guess. So what this looks like is, let's assume over the field word, how many times does Luke appear? If Luke only appears a couple of times, it's very relevant. If Luke appears hundreds of times, it's less relevant. And if Luke appears thousands of times, then Luke is not really relevant anymore at all. And then the final component that you have is the so-called field length norm, and this is also pretty intuitive. It's if your search term appears in a short field, like a title, it's more relevant than if it appears in a long field like the text body. So if you're searching for Luke and one field is short, like let's say 5 words, and Luke appears there, this is much more relevant than if you have a field that has 1,000 words and Luke appears only there. Now, where is the problem? Why are we calculating wrong? Which of my 3 components is kind of like miscalculating here? The term frequency, the inverse document frequency, or the field length norm? It's the inverse document frequency, because what we are not doing is we don't check over all the shards how many times look appears, but we only check per shard how many times look appears. So on some shards you have, or in one shard you will have something like 55 looks or so, and on another shard you will have only 1 or 2 looks. And then the 1 or 2 looks look much more valuable because they are very rare than the 55 looks, which are very common, so you don't assume the looks are very relevant there. And how we actually get the data is so-called query then fetch. So what Elasticsearch does is, let's assume you have a query coming in here on that node, and that node has, or the data that you're querying has 2 shards, shard 0 and shard 1. And then the node is forwarding the query to shard 0 and shard 1, and says like, your query says, give me the top 10 looks. And then both shards say like, hey, here's the list of my top 10 looks. Because you don't know which are the overall best ones. So if you want 10 overall, every single shard will have to give you their top 10. And you basically just give back the score and the document ID. That is the query part. And then you have the fetch part. And in the fetch part, basically, that node here says like, overall, these are the top 10 documents. And then it fetches the actual top 10 documents. So in the first step, you just figure out like, here are the top 10 results for each shard. And in the second phase, you fetch the actual documents. What you can then do is you can add another step before that, which is called DFS query then fetch, distributed frequency search query then fetch. Basically, you do a first step where you go to all the shards and say like, hey shards, how many looks do you have? And then in the second query phase, you then tell the shards, by the way, it's not just 2 looks that you think you have. Overall, it's 64 looks, so calculate that correctly. And then you have the right calculation. And then you can basically add this pretty long parameter here, but so here you have DFS query then fetch, and if you search for look then and run that query, let me scroll it over here, you can see now the top look has the relevancy of 1.5, and the last look still has the relevancy of 1.5. Now we have basically added another step before to fix the statistics, and now the looks are calculated the right way. Should you always do that? Well, this one is a bit more tricky. Here we are a bit more careful with it depends. So we've done that query. It worked out. Or before we go into the it depends, people often ask like, how much does it cost? And there is no easy way to say how expensive that is. And this is, by the way, my favorite comic for any performance-related question, especially when it's one vendor benchmarking against their competitors, because then you find similar conditions, and your product is doing very well there, and the other product is not doing very well there. And it's generally very hard to have fair benchmarks where you say, in every case, this is behaving like this, because normally it depends very much on the queries, the hardware, how many queries you have in parallel, how much data you have. All of that makes it depends, so I cannot really tell you how much overhead you will have. You will have, rather than 2 rounds basically to fetch your data, you will have another one before, so you will have another network round trip, and you will maybe have some time to, normally the data should be in memory, so it should be relatively quick, but it could be a bit slower as well. So I cannot really say like this will cost you 5% performance or 20% performance, but it will cost you a bit. And the other thing is that our documentation for this one is actually pretty clear. That you shouldn't use this in production because it should not be necessary. It's only happening here because I have my data kind of like very badly split out over the shards, and most of the looks are in one single shard. So normally what will happen, unless you have a very weird distribution of your data, if you have enough documents, your data should be across all the nodes. So then you shouldn't need to do this because all the nodes will have approximately similar data and you wouldn't run into this problem. So here the it depends is a bit of a question. And one thing that we have is first that people run into this problem and are very confused. And the other thing is every shard has some overhead in terms of performance. And a lot of people had too many shards for too little data. And that's why we changed the default in the latest major version to a single shard. And Shai, one of our co-founders and tech lead of Elasticsearch, he always says, you use a single shard until it blows up, and then you figure out, okay, I put that much data into the single shard, I have 5 times as much data, so you probably need 5 or 6 times as many shards. And that's how you would get to the right number of shards. So you start with few shards and not with many. Because sometimes people are like, I don't know what I will want to do. I will pick a random number to make this scale. And then you pick 100 shards, and this is a really bad idea, because this will cost you a lot in performance. So don't do that. So let's quickly change the data. So what I'm doing here is I'm blocking write operations so nobody can write to my Star Wars index. And then I'm taking the Star Wars index, so here I have my Star Wars index, and I shrink it down to starlet. So starlet is the small star wars, and this one has a single shard. So I basically change my index down to a single shard. And then I can search this one. If I search for Luke without the DFS queried and fetch parameter, will the score be correct for this one? Yes, because there's only a single shard, so the statistics must be correct. And I don't need any other parameters. And you can see now the first Luke has 1.5 relevancy, and the last one still has 1.5 relevancy here. If I use a cardinality aggregation for the top one term, will this one be correct with a single shard? Yes, because I'm getting the top 11 results. Since I only have a single shard, the top one result needs to be in the top 11, since it's only a single shard. So if you run that, you will also get the right result, and there's no problem. For the cardinality aggregation, the number of unique values, will this change anything with a single shard? No. This one stays the same. So here, you are still counting wrong. You could just increase the precision threshold, let's say, let's put it to 16, and then it's calculating correct. Because here it's not really broken up amongst the shards, but this is just an improvement of how to calculate the number of unique values. So we have seen those. And now, you might say this was kind of a cheap move, because what have I done in terms of the fab theory? The fast, accurate, big. I've scaled down to a single shard. So basically we are not on the big side anymore, because we cannot scale it out to multiple nodes anymore. It's a single shard anymore. So we've traded a bit of accuracy for the big. So it's still within the fab theory, it's fast still, but we've traded a bit of accuracy for the big part. And these are kind of the knobs that you can turn. But in order to kind of pick the right knobs and tune the right trade-offs, you need to understand how the calculations work in the background to do that. And that's kind of the main takeaway of this talk. You kind of need to understand how does it work in the background, and what are then the trade-offs that you can pick that make most sense for your scenario. And for some scenarios, precision might be very important. For many others, the speed might be more important. Or you want to just have a lot of data, and that might be your primary use case. So to wrap up, it's really all about trade-offs. You always say it depends, if you know what it depends on and can explain on what it depends. And we've kind of covered the CAP theorem, consistency, availability, partition tolerance, and the fab theory, fast, accurate, and big. And those are, the first one is kind of has a proper paper and everything. The second one is just a theory that we have. Maybe we'll write the paper at some point, I don't know. But these are kind of like two common trade-offs that you will run into in data stores. And this will not just apply to Elasticsearch, but to many other data stores as well. And you kind of need to pick on which side do you want to be. So, first, I have a couple of stickers back there. If you want stickers, be quick, because I don't think there are that many. Second, I normally try to take a picture with you so I can prove to my colleagues that I've been working. Because our company is fully distributed. Nobody knows where I am today. So I'll normally wave. Thank you.